Hello everyone, today I'm going to talk about the defect effects on the signal transport of an excitable software cable. A general problem in physics is how will a propagating wave traveling along a uniform medium be affected by a local perturbation? If the system is non-excitable, a defect will usually suppress the signal or energy transport of the system. But if the system is excitable such as neuron, its defect effect is usually highly non-trivial. Here we study Hodgkin-Huxley model for neural dynamics and consider locally non-uniform ion channel densities as defects. The action potential is an electric signal traveling on neurons. It is a voltage pulse generated by the opening of different ion channels. In the Hodgkin-Huxley model, there are two kinds of ion channels, namely the sodium and potassium ion channels. Now, let's perturb a homogeneous neuron to form locally non-uniform ion channel densities. Here we consider two kinds of defect shapes, the Gaussian shape on the left-hand side and the square shape on the right-hand side. Two characteristics for these shapes are the defect width and depth. In the following, the sodium and potassium defects will be plotted in blue and red respectively. This figure demonstrates the spatial temporal plot of the transmembrane voltage on the neuron around a potassium defect, as plotted by the solid red curve. The contour of this voltage is depicted in panel A, which shows that the defect is a spontaneous signal generator. The defects in panel B to F are stimulated signal generators. The defect in G can trap a signal. The right and left defects in H can reflect and rectify a traveling signal respectively. The defect in I behaves like a switch and can be turned off to blocked signals. These dynamics converge to various long-time behaviors, including fixed point, limit cycle, and quasi-periodic motion. They can be divided into different phases in a phase diagram. Transmission through different phase boundaries correspond to different bifurcations. If we combine the sodium and potassium defects, the phase diagram will become three-dimensional. In this diagram, the orange funnel is the boundary for Hofstad bifurcation. If the defect is asymmetric, it will change the signal traveling speed according to the traveling direction of the signal. This figure shows the speed value under different defect shapes. The result in this work may be related to various problems, including model study of excitable defect system in mathematics, neuron manipulation in biotechnology, research in neural diseases, and the relation between channel distribution and neuron functions. For more details, please take a look at our paper. Thank you.